So, hi everyone, and welcome to the Power Electronics class. As most of you already know me, I'm Ben Amaskarian. You could call me Dr. Ben. And for this semester, we're going to use, again, none of the courses that I teach require a textbook. If you already had a class with me, the only textbook that we have, this is recommended, it's not required. I have to change this. Is the Power Electronics, the first course by Ned Mohan. And I would provide all the materials that you need for this class. So you don't need to get the books or any other materials for the class. If you want to contact me, my email is bscarian@wttamu.edu. My office is in ECS 221J. And if you want to set up an advising, you can email me, or you want to just, you have any questions, you can email me, or you could call my office at 806-651-5248. My office hours are Mondays and Wednesdays from 10 a.m. to 11:35, or by appointment. I'm usually free in the afternoons on Monday and Wednesday as well, but I have classes on Tuesday, Thursdays. So if you have any questions, just please stop by. Other required materials for the class are the scientific calculator, the notebook to take notes, and a laptop. The course description, we would discuss the principles of a switch mode power conversion, different type of converters, AC to DC, DC to DC, DC to AC, so on. Renewable energy systems, a little bit about microcontrollers, power management, pulse width modulation, which is a very important topic, and the rectifiers and inverters, and the applications of power electronics. These are the objectives and learning outcomes according to ABIT. I think you already have them in all of your syllabus, so just please go through them. And the learning objectives for this class is at the end of the class, you'll be able to utilize technologies to be able to simulate DC to DC converters, which is an important part of that. You're going to use these converters in a lot of courses and a lot of projects that you're going to have, especially in senior design. I see a lot of students utilize the DC to DC converters for their projects. This course comes with a final project, and in that project you would be required to build a type of converter, a DC to DC converter, or a DC to AC, or AC to DC converter. It's going to be pretty simple. The requirements and evaluation for the course, 5% is attendance, which for online students is going to be a little different. The attendance is the quiz that I put after each video that I put online. I put one simple one question quiz, and if they just answer that, they're going to get 5%. If they answer it correctly, they're going to get the whole point for the quiz. So 50% is for attendance technically, and 50% is for the quiz. We're going to have a funnel project that is going to be 10%. It's going to be a physical electronic board, power electronic board. I will put some materials on how to build, if you haven't had a class with me, like an LIC or something. The PCB board, you need to build it, design it with KiCad or PSPice or any other PCB simulation tool. I'm gonna put a lot of videos and I'm gonna spend 1 week teaching you. It's gonna be it's very easy and straightforward. You would be designing and building a PCB board, very simple DC to DC converter. The PCB board, you design it and you send it. There are a lot of companies like JCBL PCBs that they will print it, and it's usually the first 5 PCB print that you print, it's for free. You just have to pay usually the shipping cost for that. But you have to start your final project at the middle of the semester at least, because usually for printing those PCB boards, it takes a couple of weeks. Sometimes you don't find the parts that you want, and those to be shipped now takes like a few weeks. We're gonna have 2 midterm exams. Each midterm exam is gonna be 20%. We're gonna have homework assignment and quiz, as mentioned. I haven't decided how I'm gonna distribute it, but depending on how many homeworks we're gonna have, probably it's gonna be 10% homeworks, 5% quiz. Again, it depends on how many homeworks and quizzes we're gonna have. The final exam is gonna be 30%. For those who already had a class with me, for the in-person, we usually have bonus questions on the exams. And for the final project, if it's a very good final project, complicated one, I'll give bonus points. It's gonna be up to 15. Sometimes I give 20% for the final project. And the scale A is 90 to 100%, B is 80 to 90, C is 70 to 80. I think D is failed for this class is 60, 70, and below 60% is F. The last day to drop the class is October 31st. I have to double check the calendar again. And for this class, you need to have a good knowledge of a few things. Circuit design, meaning circuit design is electronics, KVL, KCL, node and mesh analysis, the ability to solve differential equation is one part, signals system like Fourier transform, and a little bit about digital signal processing, digital systems is required for this class. This class may get a little difficult and overwhelmed, but I was trying to help you through the process. This is a class that it gets a little serious in electrical engineering. So, homework problem assignment. Again, when I assign a homework, usually you have 1 week. If you need more time, email me. But usually the homeworks are 1 week to 10 days after they are posted. The final exam would be a comprehensive final exam. And usually I have 20 questions in the final exams and 10 questions for the midterm exams. Again, it depends. Sometimes midterms exams are also 20 for the online students as well. Again, attendance is 5%, and I do random attendance for the classes. And if you miss the class, you miss again, the attendance point and also the quiz. So it's going to be sometimes around 15% of the grade, total grade. So as mentioned, the homework due is 1 week after it's posted. And once the solution of the homework is uploaded, the homework would not be accepted. And the homework should appear professional, and the solution should flow in a logical manner. If I can't read a homework, unfortunately, I can't grade it. Some students don't take a clear scan from their homeworks when they upload it. I can't read it, and therefore I can't grade it completely. So make sure you get a clear scan from your homeworks when you upload it. All the homework should be uploaded in a PDF format. And another thing that I wanted to mention is, and please follow the homework policies. One thing that is actually causing a lot of trouble is the use of AI. Use of AI for homework solving and in the exam is strictly prohibited. And I know some students may use it. It's good if you want to use it to learn something, get more additional information. But if you want to use it to solve your homeworks, it's going to cause you more, harm than to help you, because imagine a scenario, and I've been in this scenario a lot of times when I went for a job interview, and if it's a technical interview, they would ask you questions, and at that point, AI won't be there to help you. So try to understand the concepts, try to solve the problems, just close the book or your notes, and at first you may struggle, but engineering is not something that you can memorize. It's not like you're not studying history or philosophy that you can open a book and just memorize it. You have to struggle by solving problems, challenging yourself. You're an engineer, you have to be creative. You have to think out of the box to be able to solve the problems and try to truly learn the material, especially when you go out in the workforce. Some of these materials you may use, some of them you may never use, but something that you learn during your bachelor degrees is critical thinking, and critical thinking, innovation, being able to do multitasking is a very important part. And for those, this is a very good example of a course, because power electronics is basically a combination of 4 or 5 courses. It's power systems, electronics, digital systems, signals and system and control systems. So these 5 courses are combined in, and you can see that we have bits and pieces of different courses in this course. Again, if AI is used in the exams or solving homework problems, I would actually, I will not accept those homeworks, and you're gonna get a 0 for those homeworks or in the exam. And you're gonna fail the class. And the rest you can read about the academic integrity. You already know all of these. And the safety, if we don't have a lab, we may have 2 labs that we're gonna go, and I'm gonna just show you different type of converters, DC to DC converters, and do some very basic experiments, but it's not going to be something very extensive. So the first week would be introduction to power electronics. Second week would be semiconductor devices and switching losses. Third week would be the switch mode DC to DC converters, switching analysis, topology selection and design. And then we have this continuous conduction mode, design feedback controllers, and switch mode for DC power supply. We're going to have a review session that I would highly recommend you come to the review session. It's going to help you a lot for the exam. Then we have a study of AC/DC rectifiers. We have power factor correction. I think in measurement instruments, you already learned a little bit about that, but here we're going to dive deeper into that topic. We have magnetic circuit concepts, isolated DC power supplies, switch mode DC AC inverters and their applications, and UPS, motor drive, and power systems. Then review for exam number 2, Thanksgiving break, utility application of power electronics, and review of a final exam. And then we have finally the final exam. Do you have any questions about the syllabus and the grading system? No. Okay. So let's start with the class. Again, I'm going to post all these materials on Canvas. I'm also new to Canvas. I've used Canvas before, but again, it's a learning process for me. I wanted to submit the syllabus last week, but there has been some changes in the syllabus, and the college has sent us a new syllabus that we have to do modification to our previous syllabus. So I'm gonna upload the syllabi today after the corrections. So the outlines for today, we're gonna have introduction and the definition, applications and examples, design requirements. So for today, we're gonna go through the definition of power electronics, the industry overview and market share analysis, multidisciplinary nature of the field, block diagram of power electronic systems, the need for power electronics, types of power conversion, need for the control, figures of merit for power electronic converters, and the future trends. So for the importance of power electronics, do you know what this picture shows?
It's like
The blue lines, yes. Yes, these are the power grids all around the world. So it's the largest man-made machine on Earth, and these are just showing the grids. Obviously, you have to power the grids, you have to control the grids. There are a lot of power plants powering the grids, control station, transformers, and so on. And all of these systems must work in a synchronous manner. If one component fails, the load or the power generation, it's going to fail the whole system. I think you all remember it was, I think, the 2021 Texas power fail, North of Texas. And that, so imagine we have a large system like that, and nowadays we have a lot of renewable energy systems. The sun doesn't always shine, the wind doesn't always blow. You have to be able to precisely control all these components, and all these control systems are done through a power electronic system. So the electronics part is the solid state electronic devices and their driving circuits. The power side is the static and dynamic requirements for generation, conversion, and transmission of power. And the control part is the steady state and dynamic stability of the closed loop system. So the power electronics is defined as the application of solid state electronics for the control and conversion of power. So technically what it means, it's electronics at a high voltage. We already learned electronics and electronic devices and circuits. We learned about semiconductors, diodes, transistors, etc. But those, especially in the lab, those circuits are for low voltage. The maximum voltage that we went was about 30 volts. Power electronics is everything above 100 volts and so on. So a power electronic circuit is used to convert electric energy of the supply into a voltage or current, frequency, and amplitude suitable for user loads. This is a schematic of a power electronic system. We have the power input. Power input could be a generator, a few hundred volts to a few thousand volts. We have a power processor. That could be a converter. It could be a DC to DC or AC to DC converter. Then we have a power output, which goes to the load. So the power output, we get a sample for that. We give it to a controller, and the controller sends control signals to a power processor. From LIC, do you remember what type of system is this block? It's a feed back or a feed forward system. This is a feedback system. We get a signal sample from the output, we process it, and we feed it back and control the system. Now, one example could be this. Imagine that you're running a water pump. So the water pump, the motor is our load, and we're getting power from the grid. The power processor in this system controls, let's say, the voltage. Controlling the voltage could control the torque. And we want to maintain a certain pressure in the water. So what we can do here, we can put a voltmeter here at the power output, measure the voltage, and whenever the voltage goes up and down, because we want to have a steady flow and a steady torque at the motor, we can send the signal to the controller, and the controller can tell the power processor to stabilize the voltage. It could increase or decrease the voltage. This is also called a PID. I don't know if you heard of a PID controller, but a PID controller is an integrator, a differentiator integrator controller. They are used in a lot of different applications. One application that it's used, and I'm going to explain about it later, is thermostats to control the temperature of a room or something like that. They use a PID controller. Or to a lot of applications for this is going to be in EVs or controlling the output of a solar system. So power electronics deals with conversion and control of electrical power using power semiconductor devices that operate as high-speed electronic switches. So the power electronic part is the power processing part here and the controller. So this system is our power electronic, has the power electronic. So as mentioned, it's a conversion between the control and the electronics, or the electronics, you can say, and the power engineering. So it's a combination of electronics and power engineering. In electrical engineering, we have 4, some people say 5 main majors. One of branches of electrical engineering, and this is the beauty of electrical engineering. Nowadays, if anyone asks me what major I should pick, I would immediately tell them electrical engineering. Some people want to go computer science, and the main reason is that it's so versatile and multidisciplinary that you can pick everything. You can pick power systems, which is the oldest branch. You can pick control systems and robotics. You can pick communication systems, which deals with 5G, Wi-Fi, everything that you see, microwaves, radars, all of that is one branch of electrical engineering. And you can pick electronics. And electronic deals with from your electronic systems, your laptops, phones, and so on. But it's just expanding. One other major that in the recent years has gained a lot of traction is biomedical engineering. So MRI devices, CT devices, X-ray, sonogram, all of these is a subsection. And electronics is what deals actually with the computer engineering side as well, not the computer science part, because that's more. It's actually more related to mathematics, algorithms, and so on. But the computer engineering part, and we have a whole set of courses for computer engineering that I used to teach, which is computer architecture, which is the second book from Digital Design, Maurice Mono. Second book is actually computer architecture, that after we learn about flip-flops and cache, you learn about memory. And we already, I think, spoke about this in digital design. So counters and then shift registers, and then we go to memory, CPU, and so on. So electronics, you learn the design of transistors and how to design a computer, a CPU and GPU. What NVIDIA does is basically a part of electrical engineering. And actually the CEO has a master's in electrical engineering. Jeff Bezos also, I think, he has a bachelor in electrical engineering, and they learn programming and all of that on that side. So a lot of advancement that you see in AI, and AI obviously it affects all engineering majors, but electrical engineering again has a big part of that, and designing these GPUs and these processors for running the AIs. And another thing that is getting a lot of traction is AI in the next 20 years. The projection is it's going to consume double the power that the entire power that we are consuming right now. Yeah, double that, just to accommodate the rise in AI. So it's going to be a lot of demand for power system electrical engineering. And the good thing is, in the near future, we can replace it with AI. Can replace the power engineering with AI. So it's relatively safe at this point. And again, combining the electronics part, two majors, and the power engineering part, or power systems and electronics, and control systems as well, you have power electronics. So, as mentioned, it's the technology for conversion and processing of electric power and its application. It provides the basis for a variety of new electrical circuit architecture that allows substantial improvement in performance and flexibility. You already know how to read faster than I do. I'm sampling language, so I'm not very good at reading. So we have, again, three main categories. We have electronic switching circuits. We have the converters, which are the AC to DC, DC to DC, DC to AC, and AC to AC converters. And we have the high current or high voltage electronics. The objective of converters is to match the voltage of the load with the source, or convert one type of energy to another, meaning AC to DC, or DC to AC, or DC to... Can you give me an example of an AC to DC converter? You already had this in electronics. It was a main part of electronics class, electric devices and circuits. I'm sorry. Yes, perfect. Thank you. Great. We had the bridge rectifier. And as you remember, a bridge rectifier, what did the bridge rectifier do? I think you did it in the lab as well. We gave it an AC signal, and the output was a DC signal. Do you remember how a bridge rectifier looked like? So a bridge rectifier looked like this. This is the main type of rectifier. So my pen stopped working. So we had 4 diodes. This was our output. And you connect it to a transformer. We had an AC input. Obviously, we had other components like a capacitor and so on to get rid of ripple factor. But after adding a capacitor and an inductor, what we have is a DC signal. So we have an AC input and a DC. What was the application of a rectifier? Where do we need to convert an AC signal to a DC signal? What items require a DC voltage to charge? Which components? How do you charge your phones? all the phones you have, smartphones, laptops, all of them, you have a battery. The battery, you can't charge it with an AC voltage. You need to have a DC voltage. So therefore, you need to have an AC to DC converter. So all the chargers that you see, those small chargers are an AC, they have an AC to DC already rectifier inside them. And they also step down the voltage as well. The step down voltage is done by the transformer, because obviously you can't charge a phone with 120 volts. You need around 5 volts. So first thing that it's done, the transformer part converts AC to AC, and it goes from 120 volts to, for example, 12 volts. So you have an AC to AC converter inside, and then you have an AC to DC converter. You have 2 converters inside those chargers. One drops the voltage, which we call a step down, and I'm going to explain more. I think, have you learned about transformers yet? Okay, so step down, as you learn from transformers, it's the ratio between the turns from the primary and the secondary coil, and N1 to N2 is equal to V1 over V2. So for example, if V1 is 120, V2 is 12, and N1 is 100, what would N2 be? I want you to think on this a few minutes. What is N2? Yes. So N1 is, sorry, this is N1 is 100, N2 is unknown, V1 is 120, and V2 is 12. So N2 will be 1200 or 120, which is 10. Okay. So the voltage drops 10 times, and the current increases 10 times. Because as you know, the current ratio is the opposite. It's N2 over N1. Okay. So if our primary current was 5 amps, what would the secondary current be? 50 amps. So now you may think, so we decrease the voltage from 120 to 12, but our current has gone up significantly. Wouldn't that damage our phone? How do we protect that? What do we do? Do we add another component, or no, we don't need that? Let me put this question. This is an interesting question, and I get this a lot. Let me add another slide here. I don't want to. Okay. Imagine that we have a battery. This is my question. I have a battery that's 12 volts. This is negative, this is positive, okay? But the maximum current of the battery is 100 amp. 100 amp is actually normal. And I want to connect this to a charger to be able to charge a phone. So imagine this is a smartphone. And I want to be able to charge this. And on your charger, do you have any charger with you? Happen to have your phone charger? You don't have any phone charger? So on a phone charger, if you have a phone charger, you would see that usually it says it's rated at 1 to 2 amps, okay? Maximum. 1, 2 amps maximum, but usually it's 500 milliamp. So if this is rated at 1 amp and this produces 100 amp, would this damage the phone or not? So imagine the charger is 12 volts but 1 amp. Would this damage the phone or no? First of all, the phones have a intelligent system that they could detect over voltage or under, and they would disconnect the charging. But imagine instead of a phone, you have, I don't know, this is a car battery, obviously, it looks like a car battery. Imagine it's connected to your stereo system in your car. The battery is capable of generating 100 amps, okay? And the stereo system works on a 12 volt, but it's rated at 2 amps maximum. Would that damage the stereo system? What do you think would happen? I'm sorry? You would blow the speakers. That's a good explanation. But why doesn't our speakers blow? Good observation, but why do you think that doesn't blow? Let me put it this way. If I put a voltmeter on these outlets, what voltage do I get? 120. What current would I get? What is the current coming out of that outlet right now? 0. If we had current, we would see the electrons flow. Okay, just kidding about that part, you won't see it, but why do we see 0 current? Because this is an open circuit, okay? When you have an open circuit, what is the resistance? Infinite. What is the relation between current and resistance? Ohm's law, V is equal to IR, yes? So I is equal to V over R. When our resistance is infinite, no matter what our voltage is, what would the current be? 0. So when we have an open circuit, no matter if we have 10,000 volts, if the voltage gets very high, like 1,000,000 volts, then you're gonna have a lightning. The reason is because you have a plasma and it's gonna make air as a conductor. No, that's a different scenario. But when you have a high resistor, you're gonna decrease the current passing through it, okay? But what happens if I have a short circuit? Then resistance goes down to 0, current goes up to the maximum, and voltage drops to 0. Because you don't have any voltage difference between V positive and V negative, okay? That's the reason you have these breakers. Breakers, they are rated for a certain current. When the current shoots up, it means you have a short circuit and it's gonna blow the fuse. Okay, pop the breaker. That's the principle of how the breakers work. Usually they are a tin wire, like something like this. And when they heat up, it's just gonna burn out. Some of them, in cars especially, they are single use. In your home, you have a breaker that you can just, but in a car, and even those breakers, if you put too much current in it, it's gonna. So what happens in a phone? So what happens in the phone is when you want to charge, you have a limited resistance, you have a load. And when this load is usually high, therefore you would have the current, the maximum current I is actually V over R, okay? So if you have 120 volts, but your resistance is 100, then you would have 1.2 amps going in, okay? So the voltage is fixed by the source. Current is determined by the load. If the load has a higher resistance, you're gonna get lower current. If you have a lower resistance, you're gonna have higher current, okay? And the same thing that I mentioned with outlets. The reason that we don't have any current passing because it's air. Air has an infinite resistance, you don't have any current.
So do we normally see that load in the charger itself or in the phone when it comes to like this specific case?
So if you put a current meter on, that's a great question. Current meter on the line, one of these clamp meters, you could see that only the current is passing. So actually the load is determining. And it's the same with the outlet. I can connect a heater, a space heater here, rated at 1500 watts. It's gonna consume like 12 amps. But if I connect a LED light, that's gonna get 1.1 amps. Both of them are rated at 120 volts. One is taking 10 amps, another one is doing 0.1 amps. Okay,
Because the load is.
the load is different. The LED has a high resistor. The heater has around few ohms. That one has around kilo ohms. Okay, and I give this water terminology. So imagine voltage is the speed and the current is the amount, the current. You can have a bucket. If you have a small bucket, you can fill it pretty quickly because the velocity is the water velocity, the potential, electrical potential is actually, it's like gravitational potential. It's the difference between the electrical voltages. You can have a small bucket and take 1 milliliter, or you can have a huge bucket and put 1 gallon. Okay. Both of them, when you put it in the water, you would have the same, pressure from the velocity, but it depends on how big your bucket is. If you have a smaller resistor, it means you have a bigger bucket. You have smaller resistance, you can take more current. If you have a larger, larger resistance, you have a smaller bucket. Okay. So in this scenario, the amount of currents we take is determined by the load resistor. Now, what happens if, and this is a great question, what happens if accidentally you short circuit the load? Okay, most of these chargers have a protective system in them. So if they have electronic control system, if the current surges, it's going to cut off the power. But if it doesn't have that and you just short circuit it, it's like short circuiting your outlets. You don't want to do that. You're going to have then, because the resistance is 0, the current is going to shoot up to max. And it's going to damage the system. Also in the house, you have the breakers, you have multiple breakers to protect for that. But if you don't have that, for example, if there is a high voltage transmission line and it's suddenly connected to earth, or two phases are connected together, it's going to make significant damage to the transformer. Because suddenly you have huge current surging through your transformer or line, and huge current is going to act like a superheater. It's going to melt down all the conductors. Okay, so these are the. Now for a simple charger, we have 2 converters in it, and I will explain about, again, we're going to have one class about rectifiers again, but we're going to dive deep, especially in the control signals for the rectifier. So the multidisciplinary nature of power electronics, as I mentioned, it's comprised of several disciplines: the semiconductor devices, analog circuits, control design, magnetics, electric machines, power system engineering, circuit simulation, communication and networking, and storage. So semiconductors, actually the rise in semiconductors and the emergence of new transistors made these power electronics widely available. 30 years ago, 20 years ago, they couldn't even think of building like such a thing as a drone. The BLDC motors, the brushless DC motors that drive these, a lot of these EVs as well, and a lot of these drones, they are controlled with a DC to DC converter or a PWM. And 20 years ago, we didn't have that technology. So the emergence of drones is because of power electronics, I can say mainly. And smaller motors, more powerful motors, and the control systems that they built around them. And I'll explain a little about the drones as well, if you like, and how they operate. We actually had a group of students I think last year, that worked on a drone. They built a drone. We still have the drone in the lab. If you're interested in continuing those projects for your senior design, you're more than welcome, especially in EVs and robotics as well. And then we have analog circuits for controlling them, the control design, magnetics for relays, high power electronics, electric machines like the BLDC, brushless DC, asynchronous motors, synchronous motors that we control with controlling their frequencies, so frequency controlling systems. Power system engineering, circuit simulations, communication and network. For those who I think few of you who have worked with Xcel Energy, the transmission, distribution, every part of the grid, you need to be able to control a relay or a contactor. How many of you had measurement instrumentation with me? You all okay? And you remember we did the contactors in the lab, and we controlled those using the switch. Those are the control parts, and obviously you can't have someone having their fingers on a start-stop button all the time to control 100 switches and stations and transformers. All of that should go through a automated system. Can't have someone being awake 24/7 controlling that. And all of that is done usually through a power electronic system and storage systems as well. So power electronics, in terms of topical areas, we have the conversion technology, which is the circuit theory, conversion efficiency, switching matrix, signal processing, EMI and filter circuit, magnetic components, and rotating machines. And then we have the power semiconductor technology, the power devices, the power ICs, the drive circuits, protection circuits, and the heat sinks. And then we have the power control technology. We have the IC control package, microelectronic circuits, microprocessor circuits, digital and analog electronic circuits, control theory, the transient and stability issues, digital information, signal processing, and simulation. And these are the different topics of power electronics. And the interdisciplinary, as I mentioned before, we have the solid state physics, circuit theory, systems and control theory, signal processing, electronic, power system, electromagnetics, electric machines, and simulation and computing. Power electronic as an enabler of technology. Power electronics is the interface technology, physical and virtual, between, this is an example between a source and a load. The source could be AC, the load could be DC, the source could be DC and the load could be DC. The source could be DC and the load could be AC. And one other, the source could be AC and the load could be AC. You may ask, why do we need to convert AC to AC and why do we need to convert DC to DC? Sometimes in the source and the load, we want to match the frequency. That's the reason we needed AC to AC, or we need to match the voltage. And same thing for DC, we want to match the voltage. And where do we use these? So it's considered, power electronics is considered as one of the most vibrant technology sectors due to ever increasing applications in renewable energy, computing, sensing, and communication, IoT, and because of its overlap with many other industry verticals. Nowadays, in EVs, it's a big part of that. It's part, even in normal combustion engines. A lot of those parts, like the alternators, the headlights, the computer, the ECU, all of that. ECU is actually a power electronic system unit. It has a lot of power electronic components in it for the high voltage and the low voltage. And also in the hybrid cars, you see a lot of that. From interfacing a mobile phone battery, hybrid cars, wheels, all the sensors, connections, high voltage part, power plant, power generation, and distribution up to a nuclear reactor. Require efficient power handling from milliwatts to gigawatts to facilitate the transfer and conditioning of power from the source to the load, and to be achieved with less cost, high efficiency, high power density, high reliability, and easily. So this is an example of power electronics. Power electronics is everywhere. And it's projected by 2030, 80% of electricity could flow through power electronics at generation, storage, transmission, distribution, and end use. Here you can see a centralized generation system. It could be from coal, nuclear, renewable energy, hydroelectrics, solar, anything. We have two main sources of transmission. It could be a high voltage AC or a high voltage DC, or what we call the HVDC. High voltage DC is usually for anything above 500 miles. And the reason is it requires more components because at the generation side, we have to convert AC to DC. And at the end, we have to convert DC back to AC for household use. And the AC to DC part is actually easy. DC to AC part is a little difficult and very costly. So you may ask, why do we even use a high voltage DC or HVDC system? Reason is the loss is much less in the transmission compared to AC. It has a lot of benefits. You don't need to bundle the lines. You don't have to worry about the inductance in the lines and a lot of different, especially power factor correction. There's some issues with that. If you're able to reduce losses, you can use a transmission line that is narrower, so you're gonna reduce the material that you're using. If you are using copper or aluminum, mainly they are using aluminum, it's gonna significantly reduce costs. It's beneficial if it's over 500 miles usually. If you want to run an undersea cable, DC is the way to go. AC, again, you need a transformer. You need two transformers. You need a step up transformer, usually to step up the voltage from a few hundred volts to 400,000 volts sometime. And at the and you need to step down the voltage from 400,000 volts to 5,000 volts usually, and then down to 120 volts. So all of these control parts require a power electronics system, especially in the HVDC. And then we have the distribution side. We have the single phase utility grid. Again, all these controllers are usually done with power electronics. We have the residential, if a house is generating PV, it has a photovoltaic and generating solar energy. You have to be able to accurately control the flow of energy. Sometimes you create extra energy. You create more energy than you consume. You can sell that back to the grid. That requires a power electronic system. Sometimes you want to store that in a battery to later use it at night. That requires a power electronic system. And sometimes you want to get energy from the grid. Again, that uses a power electronic system. And if it's directly connected to a solar power system, you need to be able, the grid, you need to be able to coordinate that. Any renewable energy system, wind, solar, you need to coordinate that with power electronics. If you want to charge your EV, you need to have power electronics. If you have a metro station, subway, or electric bus, you need to convert the AC to DC. Some industrial loads use AC, a few use DC. And fuel cell generation. And another topic that is growing is these power systems, that the large storage systems that use huge batteries to store energy for later use. The market is expected to grow from 35 billion in 23 to 55 billion in 2030. The estimated growth is 7.74% from 2014 to 2026. A power electronics system consists of power electronic switching devices, linear circuit elements, digital circuits, microprocessors, electromagnetic devices, DSPs, filters, controllers, sensors, etc. An ideal switch controls energy flow with no loss. When it's on, it has 0 voltage drop and will carry any current. When it's off, it blocks the flow of current regardless of the voltage. So the desired efficiency and reliability would be 100%. Obviously, these diodes and semiconductors, you have loss, you have leakage current and reverse bias, and in forward bias, you have a drop in a voltage, usually is 0.7 volts, depending on type of semiconductor. Different type of power converters. We have the rectifier mode and we have inverter mode. If we are going from converting AC to DC, we use the rectifier mode. If we are going from DC to AC, we use the inverter mode. So the converter is a general term. An AC to DC converter is shown above. The rectifier mode of operation when power is from AC to DC, and the inverter mode of operation is from when power is from DC to AC. Power converters can also convert DC to DC and AC to AC. Practical switching devices are selected based on their power handling rating, the product of their voltage and current rating, rather than the power dissipation rating. Let's step back a little bit, and we learned that for a rectifier, for going from AC to DC, we need a rectifier, and we do that through a bridge, like a Wheatstone bridge, like a full bridge, full wave rectifier. Okay. Now, this converts AC to DC. So AC input, DC is the out. But so we're going to have an AC input, and the rectifier converts it to DC. Well, what if we want to convert the DC to AC? How can I convert a DC signal? Imagine we have a DC signal like this, and I want to convert it to an AC signal. How can we do that? Yes, inverter. Perfect. How do you think an inverter works? Okay, that's a great question. So DC, the frequency is 0. You don't have any frequency. It says yes. AC, let's say this one has a frequency of 50 hertz, okay? So you're going from something that is consistent to something that is alternating. So direct current to alternating. How can we do that? So imagine if this is 12 volts, okay? And we want to build something that goes from 12 volts to negative 12 volts. And it's alternating between that. Let's make it simpler. This is a sinusoid AC. Imagine we're going to have a pulsating. let's just forget about the negative part as well. So I'm going from this DC to this pulsating DC, which alternates between, let's say if this is 12 volts, this is 12, 0, 12, 12, 0. Both of these are AC. The upper one and the lower one are both AC. But how can I go from that direct current DC to AC? How can I make a AC signal out of a DC? I want you to think on this, and we'll get back to it in the next class. But DC to AC, we already learned. I'm sorry, AC to DC, we already know that. But how can we go from it DC to AC? Obviously, it's the device called inverter, but how can we do it? Is it a type of transistor? Is it a type of switch? What is it? The areas of PE. We have the applications, the topology, circuitry, the power electronics, the power semiconductor components, and the modeling and control. Some applications of power electronics systems are the DC and AC regulated power supplies, electrochemical processes, some of them are like power, hydrogen power cells and so on, electrolyte. And we have heating and lighting control. We have electronic welding. This is a big area. Power line, VAR, and harmonic compensation. So reactive power, we want to, compensate that. High voltage DC system, photovoltaic and fuel cell conversion, variable speed constant frequency system, solid state circuit breakers, induction heating, and motor drives. And these are some applications, again, in the generation, thermonuclear, hydro, photovoltaic, wind, conversion from AC to DC and DC to AC. They are used in data centers, AI, railway, EVs, plug-in hybrids, motor drives, switching power supplies, business machines, servers, UPS, and so on. I think it's enough for today up to here. Next week we will continue with the next class we will continue with the applications. I would post the video and the materials online for you as well to see, and also the syllabus. Do you have any questions from this class? No? Okay, thank you so much.